Okay, so we've seen that the typical energy associated with a bond or with ripping an electron out of an atom is about 10 to the minus 18 joules. That's our characteristic number. As in many ninja calculations, a characteristic number is a very useful thing to have. But how does this compare with the practical amount of energy you can get from a real energy source like burning petrol or a lithium-ion battery? Well, let's find out. Here's a chemical reaction involved in burning petrol. And it turns out this liberates about 40 megajoules per kilogram. Now you're breaking a bunch of bonds in here and replacing them with other bonds. So the energy you get from breaking these, we expect to be something like this. However, the total amount of energy you're going to get out is going to be less than this because you've also got to rebuild the bonds at the end. You're not leaving dissociated atoms at the end. And presumably there's some sort of energy associated with these bonds, which is obviously less than the energy with those bonds, or you wouldn't get any heat out at all. So we might expect an energy to come out that's a bit, maybe half or a third or a quarter or something of this, a bit less than that. Let's see. So first of all, if you've got 1 kilogram of petrol, how many molecules are there in that? Well, here's the petrol. Petrol, of course, is much more complicated than just this, but this is a key ingredient. So we've got 8 carbon atoms and 18 hydrogen atoms per molecule. Now, carbon has an atomic mass of 12, hydrogen has an atomic mass of 1. So the total molecular mass is going to be, we've got 8 carbon, so 8 times 12, plus 18 hydrogen, 18 times 1, times the atomic mass unit, that being the mass of one proton or neutron that we've seen before. And that comes out as about 2 by 10 to the minus 25 kilograms. So the number of molecules of this in a kilogram of petrol is going to be roughly 1 over that. So number of molecules is going to be about 5 by 10 to the 24 per kilogram. Okay, so that's how many molecules have had to undergo chemical reactions to produce this. But how many bonds are there per molecule? Well, let's take this. There's 8 carbon atoms and 18 hydrogen atoms. So that's roughly speaking 8 plus 18 bonds. Again, that's very rough speaking. Chemists will be curling up their toes in disgust at my crude ninja approximations here. But that's about 26 bonds. The exact detail will depend on how everything's arranged, but that's going to be not too far off. So the number of bonds in a kilogram of petrol is going to be about this times that. Therefore, the energy per bond is going to be very roughly 40 megajoules. That's 4 by 10 to the 7 joules over 26 times 5 by 10 to the 24, which comes out as about 3 by 10 to the minus 19 joules per bond, which is actually pretty close to the figure we've got up here, about a factor of 3 less, which is roughly what we were expecting. So that's telling us that the sort of energy we can get out of petrol actually has a pretty fundamental origin. It's coming back to the fundamental binding energy of electrons to atoms, which comes from the size of the atom and the strength of the electric field, which goes right back to fundamental electromagnetism and quantum mechanics. So it's going to be rather hard to get combustion that produces much, like thousands of times more energy than this. How could we get more energy out of combustion if 40 megajoules wasn't enough? Well, if you've got this sort of energy per bond, what we really need is a very large number of bonds and not much mass. So hydrocarbons are typically going to give about the same sort of energy as this. Indeed, petrol and similar hydrocarbons all tend to give 40 to 50 megajoules per kilogram. It can go up to about 55 megajoules per kilogram for methane, because the methane's a bit lighter. And for something like burning wood, it goes down, or digesting food, where there's less favourable reactions and more baggage along, it drops down to about 10 to 20 megajoules per kilogram. But that sort of figure of a few tens of megajoules per kilogram is about what you get from hydrocarbons. And we can see that goes right back to the fundamental laws of physics. You're not going to change that. You're not going to find a hydrocarbon that can have 400 or 4,000 megajoules per kilogram. The best you could do would be to combine something like hydrogen and oxygen. Because hydrogen is very light and oxygen, you get just one bond for not many molecules, and that indeed does give you about 140 megajoules per kilogram, simply because it's so light, not much atomic mass per bond, and that's about as much as you can manage for any sort of combustion. Indeed, this is sometimes used in rockets. Though it does have drawbacks because you need to keep the oxygen hydrogen cryogenically cooled. So what you gain in terms of more megajoules per kilogram, you may lose in terms of the expense and complication and weight involved in keeping everything cryogenically cold. Hydrogen fuel cells also can use this and do quite well. So that's what you're going to get from combustion. How does this compare to batteries? Well, lithium-ion batteries is the current ones of choice in most mobile phones, laptops and so on, are actually pretty pathetic. So for a lithium-ion battery, the energy density, the storage in that, is actually only around 0.9 megajoules per kilogram, compared to the 40 or so you get from burning petrol. So that's pretty pathetic, really. Why do batteries do so badly? Well, it turns out the problem here is actually not the chemical reaction. The actual chemical reaction involved in stripping ions out of lithium generates about 41.7 megajoules per kilogram. So if you just purely do that chemical reaction with the lithium, you'd be up there with the same sort of density as petrol. The trouble is, to get a practical lithium-ion cell, you also need to have electrolyte, and you need to contain the whole thing and stop it from catching on fire and reacting with the air, and all that extra stuff adds weight, which makes the difference between this theoretical maximum just for the pure lithium and the actual practical figures. So it looks like there could in principle be a fair bit of room for improvement in lithium-ion cells that might bring it up if you could get rid of all this extraneous stuff. And of course, in reality, you're not doing as well for petrol. A petrol engine doesn't just convert petrol into energy. It's got to have cylinders and pistons and pipes and fuel tanks and things like that. And so in practice, by the time you factor all those in, your total energy density is about a factor of 4 less for a typical internal combustion engine. Only if you think a typical car engine is about 150 kilograms. And let's say you filled up with 50 kilograms of petrol. So that means the total mass is 3 times the mass of the fuel, so your efficiency is about 4 times less, so you're down to around maybe 12 megajoules per kilogram if you include the engine. So that's still a lot better than you're getting from lithium-ion cells at the moment. Makes you wonder if maybe you could power a laptop off a really small internal combustion engine. That might be rather cool. So anyway, what we're seeing is that there are some pretty fundamental limits to how much energy you can store in combustion, and they go right back to the fundamental laws of physics. So you're not going to find anything that combusts is going to produce you dramatically more, like 10 or 100 times more than you're already getting from petrol, which has quite a remarkable energy density. The only room for improvement is to make the engines or all the extra paraphernalia in the cells lighter, and that could get you up to maybe 50 or a few megajoules per kilogram, but you're not going to get very much better than that.